We're going to talk here about 5.2 in our book, Modeling with Exponentials and Logarithms. So even though we can often solve exponential equations by graphing, like we've talked about calling one-sided equal sign y1 and the other one y2, and then finding that point of intersection, sometimes the numbers are so large or so small that using logarithms works better, and it may be much more efficient and quicker. So some equations, on the other hand, cannot be solved using logarithms. So really we need to understand both strategies and be able to use both strategies and decide when one is more appropriate than the other. So here we're going to work, at least in the beginning, by using our logarithms. So city A starts with 100,000 in population and decreases by 1.3% per year. City B has 70,000 people in it and grows by 3.4% per year. When will city B catch city A? So for city A, we're going to have that its population is going to be equal to the 100,000 that it starts with. And then since we have a 1.3% growth, that's going to be 1 plus that r, which is going to be 1.013 to the t power. And for city B, it's decreasing, so let me switch that. That's going to be a 1 minus 0.13, so that's going to be a 0.8. Let's see, I got to do this 1 minus r 0.013, so that's going to be 0.987. 0.987 to the t power. B is the one that's growing, so it's going to have a population that is equal to 75,000, and then that's going to be a 1.034 raised to the t power. And our question then is, when are they equal to each other? So we will set them equal to each other. 100,000 times the 0.987 to the t power equals 75,000 times 1.034 to the t power. So we can divide by the 75,000 on both sides. And when we do that, then let's see, 100 divided by 75 is going to be, I think, 4/3. So I'm going to leave it as 4/3 for now. And then we can divide this 0.987 t to the other side. So 0.987 to the t. Now is where we're going to have to use some properties of exponents here. And we know that if we have two powers that are raised to the t, we can write that as the 1.034 over 0.987 whole thing raised to the t power. So we have this maybe strange and a little bit messy number, 1.034 divided by 0.987 raised to the t power equals 4/3. So we can then take the log of both sides, and it doesn't really matter what logarithm we choose. And so that's going to become, that's going to become the log of 4/3 is equal to, and then we'll use our properties of logarithms to bring that exponent out in front and call that t log of 1.034 over 0.987. So messy as that is, that's just a number times t. So we're going to divide by that logarithm of 1.034 over 0.987. So all of this stuff is going to go into our calculator as one entry. And I'm getting 6.184. 6.184, and that would be in years. So in a little bit more than 6 years, the City B is going to catch up to City A in the population. Okay, on to the next one, doubling time. So we're going to find the time needed to double a salamander population given by P of t equals 150 times 1.125 to the t. So to double that population, then we want it to be we can see the initial population at time 0 there is 150. So to double the population means we want it to be equal to 300. So we're going to put 300 in where the p is, and that's going to be 150 times 1.125 to the t. We can divide both sides by the 150, and since 300 divided by 150 is 2, that's going to make 2 equal to 1.125 to the t power. We can then take the log of both sides, and that will allow us to bring that t out in front, the exponent out in front. So we have the log of 2 is equal to t log of 1.125. And then, as we saw before, we can divide by that log of, what did I say, 1.125. And that's going to go into our calculator. And I'm getting 5.885. 5.885, and I didn't really say time in there, but let's just imagine it's going to be years. Okay, then on to the other questions. What is the growth rate? So we know the growth rate is going to come from this base, which we know is going to be 1 plus r. So if we subtract off that 1, we're going to get a 0.125. And if we then move that and change it to a decimal, we're going to get that the growth rate is 12.5%. And how long will it take to quadruple the population? So what we found with the doubling time being about, that 5.885 years, so almost 6 years to double, then it'll take another 5.885 years to double again, and doubling the doubling is going to make that be the 4 times. So I'm taking the answer on my calculator screen times 2, and I'm getting 11.7, it's 698, so I'm going to go 11.770, 11.770, and I'm going to stick with the time being years. Okay, let's go to the next panel. And here we have a half-life problem. So carbon-14 decays at an annual rate of 0.0121%. Show that the half-life is about 5,728 years. So we're getting that the amount after t years is going to be our initial amount, which we don't know, and it's going to be a 1 minus, and if we change that to a decimal, it's going to get really small, so it's going to be 0.000121 raised to the t power. We want to know the half-life, so we want to know how long will it take, what's the t value going to be when the amount we start with is half of what it is now. So that would make that amount be 1/2 p, or you might call it 0.5 p. And let's see, what is that? 1 minus 0.1230121 is going to be 0.999879. 0.999879 to the t. So it turns out then we can divide out that p. It doesn't really matter how much we started with. It's still going to take the same amount of time to get to half as much. So we can take now the log of both sides, and I'm going to just use this opportunity to use some properties of exponents on that left side there. And then we're going to get the log of 0.999879 to the t power. So on the left side, we can say that the log of a fraction is the subtract the logs, log 1 minus log 2. Here we're going to bring the t in front using that property of logarithms and leave the rest of it the same. And you don't have to do all this, but it's kind of nice to refresh our memory. The log of 0, the log any base of 1 is 0, so that's going to be a negative log of 2. We're going to divide that by the log of 0.999879 in order to get our t, and let's see what that is. And I'm getting 5728, 5,728.143, And so that is approximately 5,728 years, like we were supposed to get. On to the next one. So now we're changing from p's to q's. So q of t is q sub 0 e to the kt. And now we're switching over also to looking at this, what we call continuous growth. So if it's decay, like we are in half-life, then that k is going to be negative. That's how we get decay with exponential base Euler's number. So if we have a half-life of a substance is 11 minutes, we're going to solve for that k. So like we did before, in 11 minutes, when the time is 11 minutes, we're going to get half of what we started with. Q sub 0 was our starting amount. Half of that is going to be half of Q sub 0. And that's going to be whatever that Q sub 0 is, e to the, and then we're going to plug in 11 for that t. So that's going to be 11k, and we know that we're counting time in minutes here. So again, it doesn't really matter what you start with, because that Q sub 0, that initial amount, is going to divide out. So we're trying to solve 1/2 is e to the 11k. Now, because we have an exponential base Euler's number, we want to take a natural log of both sides. And that's going to get us to the natural log of e to the 11k on the right side. You don't have to, but I'm going to go through these properties of logarithms again. I think it's important to reinforce those. And so that's going to be the natural log of 1 minus the natural log of 2. Now, a logarithm-based Euler's number and an exponential-based Euler's number are inverses of each other, so they are just going to cancel each other out. We know the natural log of 1, the log any base of 1 is 0, so we're going to get to the negative natural log of 2 divided by 11 is going to be our k. And so a negative natural log of 2 divided by 11 looks like a negative 0.063. Negative 0.063 to 3 decimal places. And we would expect a negative because it's decay, and it's going to be slow because yep, I think that's about right. Okay, converting between, like we talked about in the other examples before, we want to be able to convert from our annual percent increase to an exponential and back. So if our base is the b, then you can, when we're trying to convert those, you can just kind of focus on what it is that is being raised to that t power. So we'll get b is equal to e to the k, and we know that to solve that, we'll take the natural log of both sides and get that k is equal to natural log b. So in our conversion, this is one we looked at earlier, if this is our exponential base b, and we want to convert that to a continuous growth rate, then we will take our b, that 1.125, and set that equal to the e to the k, which means we're going to take the natural log of 1.125, and that's going to be the natural log of e to the k, which is going to be k. And on our calculator, if we take the natural log of 1.125, then we'll get a 0.118 to 3 decimal places, 0.118. And it's positive because this is growth, because our original was 1.125. And you can see that it's close to what we got. So the 0.118 is close to that 0.125, but a little bit smaller because we get more kind of bang for the buck when we're a base Euler's number. Now we're going to go the other way, and we're going to try to convert this exponential base Euler's number into just an ordinary base. And so we can see that when t is 0, e to the 0 is 1 times 4 is 4. So the easy part of this is to know that a is going to be equal to 4. The harder part is, but not too hard, is to say that e to the 0.2 is going to be equal to b. So there is no need for a logarithm here at all, because we can just punch that into our calculator, and say e to the 0.2 power, I'm getting 1.221. 1.221 is the b, and we can leave it there. If they had asked us, which they didn't here, about the percent, I don't know what I had. Did I have more problems there? I don't think so. Then we could have said here that the percent is going to be 22.1% growth, whereas you can see this would have been a 0.2 would be like a 20% growth. On to the next second. Did I really not have more? I thought I did. Nope, guess not. Okay, let me go back into the next panel. So here's some more examples. Let's see if we can convert the 300 times 0.795 to continuous growth. So that means we want to take this base right here, and if we want to be continuous, then we want that to be e to some k, and we want to find out what the k is. So we'll do that by taking the natural log of both sides and recognizing that that's how we're going to get the k. And on our calculator, if we take the natural log of 0.795, I'm getting that to be a negative 0.229 to 3 decimal places. So there is our k. And if we wanted to write the whole thing, it's optional. I didn't really ask that. But the initial value, 300, would still be the same, regardless of whether it was written as continuous growth or annual growth. And we would get the negative 0.229 to the t. So here's our growth, our decay equation written with a base Euler's number, which is equivalent to, that's exactly the same values as our annual growth, or annual decay in this case. Okay, assuming growth rate is exponential, if the population of a city grows from 12,000 to 15,000 in 4 years, can we first find the annual growth rate? So if we're just thinking annual growth rate, we're thinking that we're going to have A equals whatever the initial amount is, and it's just going to be 1 plus r to the t. So that's going to be our equation to start with. We know that we're going to say 12,000 is the population. We're going to call that times 0. So that's going to give us A equals 12,000 times the unknown 1 plus r raised to the 0 power. And so that's going to tell us that that A is 12,000. And now we're going to try to solve and find out what the r is, and we'll use our other point there. So that's going to be, since it's 4 years later, we can think of that as when t is 4, the population is going to be 15,000. So we'll put the 15,000 in for the amount A, and we'll now know that our starting amount, our initial amount, is the 12,000, and this is going to be 1 plus r, and the value of t is going to be 4. And so this will now allow us to solve for r. So we will divide by that 12,000 on both sides. So we can cancel those 3 zeros, and 15 twelfths is reduces to, let's see, 3 goes in there, 5 fourths, or if you want 1.25, either way. You don't have to do this because it's all going to go into our calculator in a minute here anyway. And that's raised to the 4th power. We'll take that 1.25 to the 1/4 power to get the 1 plus r. And so 1.25 raised to the 1/4 or 0.25 power, I'm getting 1.05737 is equal to 1 plus r. That means the r is going to be, if we subtract off that 1, 0.05737, and that means as a percent, that's going to be 5.737%. So that is our annual growth rate. Now to get the continuous growth rate, then we're going to start with our PE to the, and you can either call it K or RT. If PERT is fine, if that's the way you remember it. I'm going to throw it in as K, but that's interchangeable. Again, at time 0, we're going to get that the 12,000 is going to be p times e to the 0. So that's telling us that our initial value is going to be 12,000. That's going to make our equation be 12,000 e to the kt. We'll plug in our 15,000 for the a, leaving the 12,000 as the initial amount, and that's going to be when time is 4, so that will give us a 4k. Again, we're going to divide by the 12,000 first, so that's again going to be, 5/4, or 1.25 is going to now be e to the kt. We'll take the natural log of both sides, and taking the natural log of e to the k, we knew the t was 4. Let me change that. So that's actually 4k. So that's going to be equal to 4k. So our k is going to be the natural log of 1.25 divided by that 4. And the natural log of 1.25 divided by 4, I'm getting to be a 0.05578 when we round it, and that's going to be, then k is going to be 5.59%. So very close to the same thing that we got with the other one, with the annual growth. Okay, now on to the next one. So here's where I had some more. Okay, one of these screens went down below there. So if 19% of a radioactive substance decays in 6 hours, what is the half-life of the substance? So it doesn't matter if we want to think of that as exponential base Euler's number or not. We can do it either way. Let's just maybe use our y equals ab to the t. So we know that a is that initial amount. That's what we would have at time 0. When we plug in 0 for the t, we're going to get just a. So if 19% decays, that means we still have 100% minus 19% is 81%. So that means we have 0.81 times that initial amount a after 6 hours. Now, we don't know what that a is. That's okay. The b we don't really know, but this is going to be a 6 for the value of t. My b's look a lot like my 6's. Let me see if I can make that look more b-like. Okay, so we can still, it turns out it doesn't matter what we start with because we're going to divide that out anyway. The interesting part is we're going to get 0.81 is equal to b to the 6th. So we can raise both sides to the reciprocal power. And when we do that, we're going to get 0.81 raised to the 1 divided by 6 is, on my calculator, 0.965. That's 0.965 rounded to 3 decimal places, which is going to be our b. And so now what we want, and I'm going to write that rounded, but I'm going to use the exact value on my calculator. Now we want to know that we know the growth rate right here. Now we want to figure out the half-life. So now what we're going to do is say if a is our initial amount, we want to know when will there be half of that initial amount. And so that's going to be our 0.965, and we're trying to find out what the value of t is. When will we have half as much? So we'll divide that out again, and we will then take the log of both sides, and we're trying to solve that for our t. So who can resist using these properties of logarithms? And that's going to be a t log of 0.965 so far. Log of 1 is 0, so we have negative log of 2 divided by the log of 0.965 is going to be our value of t. Now, when I punch this into my calculator, I'm not going to use the rounded value of 0.965. I'm going to capture that decimal that's on my calculator screen. So I'm going negative log of 2 divided by, I'm going to go up arrow, hit enter. That captures that whole thing. Whoops, I forgot the logarithm. So let me try that again. Let me do the negative log of 2, and I'm going to divide that by the log of, and now I'm going to go up arrow, capture that, and then hit enter, and I'm getting 19.736. And remember, our time here was in hours, so that's going to be 19.736 hours is the half-life. Okay, so on to the next one, an exponential growth problem that cannot be solved by logarithms. So our population is given by P of t equals this, but our food supply is given by a linear equation. So this will run out when our population, after our population first is equal to the food supply, and then from that point on, somebody's going to go hungry, and we're going to have a problem. So we can here, doing logarithms does not work well here. So instead, we're going to have to enter those in. So I'm going to put in this side as y1 and this side as y2. Now I'm going to pick a window here that worked for me pretty good was to choose the x-min to be 0 and the x-max to be 250. And then I said the tick marks are 50. And then for the y-min and y-max, I went from 0 to 150 and made the tick marks 50. So then when you graph that, you're going to see where it's going to look something like, I'll try to reproduce that graph here a little bit. So the exponential is going to look something like this, and the linear is going to look something like that. And we are trying to find that point of intersection. So when we do that, I'm going to go second trace down to option 5, which is the intersect. I'm going to hit enter and enter because my curves are right. I'm going to move the cursor using my right and left arrow to get a little bit closer to that point of intersection, then hit enter again. And I am getting t is equal to 87.699 when I round to 3 decimal places. And we weren't really given that. I'm guessing that's going to be in years. So that means we've got about 87, 88 years to try to figure out how we can get more food or limit our population growth. Very good.